Hello again, 114. Today we're going to be covering section 4.3. The packet. I have two of basically the same diagram, but one of them is filled in, so I made it available on Canvas. This is the information I want to go through with you for today's section, the modern place value systems of numeration. It's really these three that you see here, binary, octal, and hexadecimal, that is the most important. I initially made this blank worksheet. It's still there to have you copy the information as we discuss it, because I genuinely feel that if you write something, you're more inclined to remember it. But for the sake of expediency, I have it also filled in. What would be more important to you are these three models as we go through these examples today. Okay, so I would print this even without the information there, just because you want that much. Okay, then there's a reference table I made of different systems, those that we have discussed and those forthcoming, and what the positional values would actually equate to. And so print that out. And this is going to be useful for conversions between different base systems, especially when we get to section 4.3. Okay, so we're in 4.4. We're in 4.3 now, but one is contingent upon the other, the information. Here is something I swiped from another resource. It's when we get to binary, you might find this especially helpful earlier on. For the sake of reference comparisons, you know that you're headed in the right direction. And then there are the actual examples. Okay, so we'll go through these together. I think that's it. Yes. All right. Let me adjust the lights as always and fire up the projector here. Walking up the sun like a supervillain. That looks like it's pretty good. I don't think I'll have to move it too much. Maybe I'll leave that alone for once. Alright, as always, here is our front page when you open our Canvas course tile. And if you want any of these diagrams, I'm skipping around, sorry. Pages, please. They would be under, this is the student view. So, under chapter 4 materials, we're still in 4.3, of course. Right. They're part of this chunk that you would see here. I actually just added this one today, so it's going to be where it says new. I had done them in blue, but just because this is something I did today, I made it black. This is the filled-in diagram. And it includes the models that are on the blank page. It's a landscape version of the portrait. Okay. Now what I want to do is go back to this diagram, which is the overview diagram. Just to reiterate, because it's helpful, I think. Remember the ancient systems that we had discussed, additive, multiplicative, and ciphered. These were all section 4.1. Positional systems that we got to last time are also ancient, so under the same heading here, but they are positional systems of note. These were section 4.2, and now we're going to be covering the modern positional systems. So they're going to behave somewhat in terms of how you calculate them as Babylonian and Mayan would. Although a little bit better, I actually think, because they're true positional systems versus these are kind of bending the rules a little bit. These are section 4.3, all right? Our modern system, the one that the world uses, Hindu-Arabic numeral system, all right, is in fact a positional system, all right? And we're all well acquainted with that, of course, but this can be translated into binary, octal, hexadecimal as just 3 examples, all right? Also others as well. All right, what you'll see is, let's see if I can find that diagram. Here's a table included that you might find helpful. All right, these are a reference table I tried to compile, all right, of the various systems you're inclined to see. Again, Hindu-Arabic, of course, our system. I'm going to get rid of the mess here. And what the positional values would equate to. The 0th power of 10, because we are a decimal system, all right, would equate to the amount of 1. 10 to the first would be 10, of course. 10 squared would be 100. 10 to the third is 1,000, and so forth. When it comes to powers of 10, as you see here, the exponent is the number of zeros. Right? So if you have 10 to the third, that's 3 zeros you would expect after 1. If you have 10 to the fifth, that's 5 zeros after the 1. The 0th power, logically, all right, if it's 0, that means there are no zeros, it's just a 1. Okay? It's a bit too bright still, so let me make it a bit darker, hopefully. Okay, sorry for the glare. All right. That helps a little bit. Babylonian we had gotten through. Thankfully, the scope of the numbers that they were inclined to deal with were not too much beyond 216,000, but that's what 60 to the third would be. 60 squared would be 3,600, 60 to the first is 60, and 60 to the 0 again is 1. Notice that pretty much down in the column here. Anything to the 0th power, with the exception of 0 as a base itself, which we're not considering, equate to the amount of 1. All right. The Mayan system, just underneath that, vigesimal, a base 20 system, quasi base 20, because yes, it does involve powers of 20, but after 20 to the first written the first time, there is a second instance of it times 18. Right, again, this is for the sake of conforming to the Mayan calendar. All right. Now, the newer things that we're inclined to see, all right, are again binary, octal, and hexadecimal. All right, these have to do with computer software and hardware. All right. Firstly, binary. 2 to the 6th is 64. 2 to the 5th is 32. 2 to the 4th is 16, and so forth. I didn't do these other ones that are beyond them because I left you some work if you want. I'm sorry, not to belabor you, but it's really 2 to the 6th that you're probably more likely to use, not 8 to the 4th. But you could figure it out. This is the pattern: 8 to the 0, 8 to the first, 8 to the second, 8 to the third, and that's what they equate to. 16ths, hexadecimal base 16, same thing. Beyond 16 to the second, I hope you don't have to do it too much. But that would be 256, 16, and 1 again. All right. I tried to include the names here because they're interesting, the nomenclature, right? Our system, Hindu-Arabic system, is decimal. Babylonian is sexagesimal, I believe is how it's pronounced. Mayan is vigesimal, or vigesimal, depending upon your accent, I suppose. Binary is binary. Octal is base 8. And hexadecimal is base 16. There's also duodecimal, which is base 12, and other incidental things like that. But these 3, as I mentioned, are the most important, I would argue. Okay. All right. Now, here again, this is a sheet that I'll back it off just a bit so you can see the whole thing at once. This is what I would give a person in person, all right, and then so that they can write information that occurs to them as being important as it's being discussed, because you're more likely to, remember things. I included this anyway, because you can still do that if you'd like, but what I want you to take away from this, if you don't print anything else, is the models that we would need for the binary system, octal and hexadecimal especially. Okay? Now, as far as the information that would be put here is concerned, let me give you that as the completed diagram, and then I'll discuss it. And I'm going to obscure part of it. So let me just do this first. Okay. All right. Here are the modern place value systems of numeration. I think I might just move this over a hint that way. There you go. All right. And we'll go through this. Let's start with the character sets that you would work with, right? Fancy braces, right? All right. The decimal system, i.e. Hindu-Arabic system, all right, includes characters 0 through 9, separated by commas because that's better etiquette. I don't always write the commas myself when I'm teaching because I think it makes it a little bit harder to read, actually. But if it were typed, in theory, that's what you should do. Base 10 is 10 with an exponent little x there, because that could be 0, 1, 2, some non-negative integer. Okay. The character set for binary is much shorter, all right? The reason why it is important to computers is because these are two different conditions, right? Two different states of being, on and off, you will see, all right, when it comes to actual computer hardware, right? If I was smart, I would have actually dug up my transistor collection, because I do have them, and I could show you what it looks like physically, but it's a little electronic component. Anyhow, we'll get to it. Base 2 would be 2 with a superscript exponent of what have you. It's really going to be either 0 or 1. Or 2, well, pardon me, the base can be anything 0 or higher that is a positive integer. Okay? So 1, 2, 3, 4, whatever. But when you're actually writing values in binary, it's just a pile of zeros and ones. All right. The octal system, all right, is characters between 0 and 7. Right? Remember, it's always one number shorter than the base number. So if the base is 2, then you stop at 1. If the base is 8, then you stop at 7. All right? Just like base 10, we stop at 9. All right? There's 10 of them total. We start at 0 in all cases. Hexadecimal, base 16, all right, goes from 0 through what would be 15. But what you have to remember is that for the sake of computer memory, especially back in the day, all right, they would need to use a one-character wide symbol, like the letters of the alphabet, to represent the concept of what would be 10, 11, 12, 13, 14, 15. All right, so essentially what I'm getting at is that when you see the letter A, just realize that A represents the amount of 10, right? B would be 11, C would be 12, D is 13, E is 14, and F is 15. So in the set, you're not going to see anything higher than 15. Right? It's just efficient to have one character rather than two to represent the amount of something. Okay? So moving on up here, or down, let's consider these things. Now, the Hindu-Arabic system, a fun fact about them is that they were invented in India, right? That's why the term Hindu, all right? Why Arabic? Because the Far East and Near East, via trade, communicated with one another, right? And Europeans who finally got on board with algebra in the Middle Ages borrowed the number system that was practical to algebra, namely the Hindu-Arabic system, from North Africa originally. Right? So what would be Arabia and any sort of colony of that. Right? So this is from the very early Middle Ages, so about 650 CE, all right? Otherwise known as AD, and further developed by the Arab algorists, all right, which is what the term algebra is derived from. All right. Binary is used in computer science because, again, these represent two different conditions of a physical thing. All right. I'm not going to do it any justice, but transistors come in many shapes. A lot of times you might have seen transistors that look like a little box with a hole in it. It's for a screw, all right? And it might have 3 legs on it, all right? It's a little electrical component, depending upon the type of the transistor, really, but some of them have more legs than this. I think 4, all right? Anyhow, a base, a collector, and emitter, all right? You can kind of think of it as being an input and output in the ground, but I'm not doing it any justice. The way that you can make the transistor behave, not exclusively, right? But the way that you can make the transistor behave is literally like a switch, right? The truth of the matter is, if you are interested in electronics, which it is fascinating, right? A transistor replaces an earlier component, at least, known as a relay. Relays still exist and they're used in cars. All right, it's basically controlling an electromagnet, all right, using a very small amount of electricity so that you don't have to touch the switch, all right? It's sort of a remote control, if you will. You use a small amount of current to operate a large amount of current. That's the basic principle of a relay upon which a transistor is based. Anyhow, if it's behaving like a switch, you can imagine this as being a switch in profile. In the off position, when essentially there isn't as much current, it's probably a little bit, but let's just call it off for all intents and purposes, that is the state known as 0, all right? And when it is engaged, when current is flowing, all right, that is the state in which the circuit is on, all right? So we would call that 1, right? Deep down into the guts of a computer, or maybe more accurately, the processor of a computer, which there are potentially billions, if not more than that, transistors, lots and lots of switches, all right? That's really what they're doing, all right, in sequence with one another, all right? They're either on or off, all right? All right. Now, these other languages exist, octal and hexadecimal, because they're sort of the bridge from the physical component, which is hardware, to the software, right? All right. A bit of data is either a 0 or 1, the on or off amount representing the data, all right? A byte of data would be a chain of these switches, all right, essentially, on or off. Here's an example of the difference between these two systems, at least. What we think of, well, 71 would be the amount that we know and love, right, in the Hindu-Arabic system. How does the same quantity appear using just 1s and 0s, right? How does the same quantity appear using the octal set instead, where the numbers that you're allowed to use are just 0 through 7 instead? These look obviously drastically different. That's a lot wider, a pile of bits, if you will. 1, 2, 3, 4, 5, 6, 7, 8. All right, that's 1 byte, and it's just 0s and 1s. And this is the same quantity using a different system. It just coincidentally has some similar looks, 1 and 0 namely, right? But there's also a 7 here, right? These, because of the models that we employ, equate to what we are familiar with, the number 71, just as an example, right? This is Hindu-Arabic, this is this is binary, and this is octal version. They all represent the same amount, all right? Going a little bit further, we have here the hexadecimal system, which is what basically software is derived from. Think of binary as being the most basic form of hardware, and hexadecimal being the most basic form of software. All right. For the sake of efficiency, remember, when letters are included after 9, they are used in place of the amount of 10, the amount of 11, 12, and so forth. All right, i.e. as a 1-character symbol rather than 2. All right. All right, now moving up, down again. Here's some more information. I could probably get rid of this at this point. Positional values are all powers of 10, of course, in the hexadecimal, in the decimal Hindu-Arabic system that we're familiar with. I'm sorry that this is far away. I just wanted to show you the whole thing at once, but sometimes it's better to see the entire forest and not the individual trees. All right. Binary is the basis of computer hardware again. All right. And the intermediary would be the octal system. All right. Byte of data is, again, a chain of bits, so a chain of zeros and ones. That's a whole byte right there. All right. And 8 bits would equal 1 byte, just for reference. All right. Conversion is how hardware translates to software, ultimately, right, in this process. Hexadecimal is essentially, just for an interesting fact, the basis of computer languages like HTML, JavaScript, and, say, CSS. Okay? All right. Now, let's get into the weeds here. As far as the models are concerned, okay, and I'll zoom in on that. These are what you're going to employ, all right, when you're translating from the system, the alien system, to the Hindu-Arabic system. You're going to take the position of the digit that happens to be 1 or 0, and ultimately, working right to left, multiply by a power of 10, a power of 2, 0, and then building it up. All right? You're going to add that, figure out that with the 0, whether you have 0 or 1 in this position, that would be the second digit in a string. All right, times 2 to the first, and then add that 2 again. Whatever the digit is, 1 or 0 in the third position, the third digit in a string of 1s and 0s, all right, times 2 squared, and so forth and so on. I put the ellipses here to indicate the pattern would continue. All right. Again, you're dealing with octal system, and you're converting to Hindu-Arabic. All right, just remember you're going to have a character that's going to be something between 0 and 7. All right, but you're going to start again at the 0th power, right, of base 8 in this case. So that times 0 to the 8 to the 0th, which is really times 1. All right, 8 to the first, 8 to the second, and so forth. Again, ellipses, because if you had more digits, you would need more of these sort of chunks. All right, hexadecimal would be characters you will see from 0 to F. There is an added thing that you have to worry about here. If you have an F, all right, just realize that F stands for 15, all right? So you would have to multiply 15 times whatever the power is, all right? In this case, the 0th power of 16, all right? If you had a letter A, then you're going to be multiplying 10 times that, okay? Those are the models. Just for the sake of analogy, when we did Babylonian and Mayan, they had their own, sort of system similar to this. Let's do some examples. Okay. Oh, geez, I didn't want that, sorry. Yeah. Here's that basic set of instructions that I was showing you last time. I'm still going to be using this basic idea, alright, again, only now the alien system is not limited to Babylonian and Mayan. It might be binary, octal, or hexadecimal, or some other base system, right? Right. Anyhow, the idea of going from whatever the alien system is to our familiar system of Hindu Arabic, all right? That's going to involve multiplication ultimately. And we have to use whatever the model is, whatever the base is, all right, to get from here to there, multiplying. All right. What would be helpful is to go about, especially earlier on, is again these same steps. All right. Identify the character set of the alien system. Kind of keep it on hand or within view as a reference. All right. And if you have a base system that's greater than 10, it really should be greater than 9. Yeah, that's technically true. Use capital letters for 10, 11, and 12. So like the hexadecimal system is really the first time that you would see that, other than maybe duodecimal. All right. Identify the number of digits or groups that you have in this instance, because we're not dealing with weird alien hieroglyphics like the wedges and the boomerangs, all right, anymore. Now we're dealing with digits that at least look familiar. We would have to, instead of looking at groups per se, look at the number of digits, all right? That they're Hindu Arabic numerals, but they're just a different system, all right? Incidentally, to distinguish one system from another, all right, you're going to start seeing subscripts, all right? So if you were base 2, then as an abbreviation, they'll have the number, but they'll put a subscript in context to identify it, to distinguish it from, the system that we know and love, Hindu Arabic, right? Why? Because we're still using the same characters. Right? It was a little bit easier in certain respects when we were dealing with Babylonian and Mayan to not have to, bother with the subscripts, because the character sets were so drastically different, right? They didn't look anything alike, really, other than maybe the number 1, Right, so just be mindful of that. They will put subscripts to distinguish one system number from another system number. Okay. We're going to write out the powers of the alien system in as many places. All right, starting with whatever the base is to the 0. All right. And then we're going to have one of those models to use. Okay. And we're going to multiply and add a lot. Okay. All right. Then eventually what we'll have to do is convert from the familiar system to whatever the alien system is again. All right. So I wonder if it's appropriate to mention this now. Here's just a useful thing when you're converting between different base system numerals. The numeral in the alien base, all right, when it is the same, right? All right, the numeral in the alien base is the same as the numeral in base 10 if, all right, n is less than the alien base. If the number here, right, is smaller than the base number, all right, and the alien base is less than or equal to 10, right? That's going to be useful later. I imagine it's probably confusing right now. What does this mean in a practical sense, though? It means when translating binary it means that the 1 in binary is still 1 in in Hindu Arabic, base 10. 1 is 1 and 0 is 0. All right. When we get to section 4.4, all right, that would be helpful. All right. So I'm just touching upon it right now, even if you don't feel super confident about it. Don't worry. All right. You haven't done any examples yet, so let's do that. There they are. Okay. All right. I left the solutions as always because I think it's more helpful to go through it with that available to confirm or deny the correctitude of our answers. All right. So let's start with this. All right. Seems a bit dim, doesn't it? We're going to convert from base 4 now to base 10. All right. Notice if it's not too obvious, let me just maybe zoom in just a wee bit here. Sorry. The curtain should not be drawn. We're going to convert the numerals, the quantity 312 in subscript of base 4 into whatever it would equate to in base 10. This essentially means we're going to translate, my black doesn't work today. We're going to translate, that's a little bit better, 312 base 4, right, into a Hindu Arabic equivalent. Okay, so what does that mean? It means essentially we're going to translate something that is alien into something that is familiar, right? And when you follow that train of thought, which operation ultimately are you using a lot? You're going to multiply. That's the most essential ingredient here, right? So, if we're dealing with base 4, let's do ourselves the favor of identifying what the character set will look like. Characters, the set of base 4 is going to be always starting from 0, 0, 1, 2, and 3, right? It's always that many digits wide, if you will, in a roster. 1, 2, 3, 4 things. And if you start at 0, you're always going to be one number shy of the base. This is base 4. Okay. All right, now, that's the set. All right. How many places, or how many digits in this regard? If we have 3, 1, 2, 1, 2, 3. We have 3 places, right, to account for. So now what we should do is write out the base starting from the 0th power from right to left. That's always hard for a Westerner, right? Because we're not used to writing in that direction, but we can do it. All right. This is 4 to the 0. This is a bit faint. 4 to the 1st, that's much better. And 4 to the 2nd. All right. Let's figure out what these would equate to. 4 to the 0th would be the amount of 1. That's the positional value. Okay. 4 to the 1st would just be the base 4. It's just 1 4 versus 0 4s. All right. 4 squared would be 4 times 4, right? So that would be the amount of 16. Okay. Now, I didn't give you the model specifically for base 4, but we can infer what it would be, all right? So here's a basic model. For this situation. We're going to have something times essentially 16 plus something times 4 plus something times 1. Okay? What is that something? The something is going to be 3 for this particular one. 1 for this particular, what would be a group, right? And 2 for the first one, really. Right? Now we'll do the arithmetic. Remember, you do your multiplication, really, before you do your additions. Right? Hopefully that's not in the way. 2 times 1 is just 2, naturally. 1 times 4 is just 4. And 3 times 16 is 48. Right? So if you add 48 to 4 plus 2, you get 52, 54. Right? That means that 312 base 4 is equal to 54 in base 10. Okay. It's not too bad, right? We have a system at least for getting to it. Right? The more that you, it could start out being like, this is insane. All right. Remember, your brain can adapt to any alien system. Right? It just requires a lot of practice. So if you feel a little sketchy about this, don't feel bad. All right? It takes a while. All right. All right. Let's do another. Okay. You notice that I write in different colors. I do that because I'm hoping to add some kind of contrast to the various steps in the thought process. And although it kind of slows the writer, namely me, down a bit while I'm doing that, I would nonetheless do that even in a classroom with a regular blackboard, right? Because you want to, catch the most fish, namely the students, by making it as easy as possible for them to see distinction. Right? They'll learn it more readily. Okay. Whatever it is that you're talking about. All right. Now, still doing this. We're going to convert what looks like 6053, but it's in base 7, to base 10. What is base 10? The system that the decimal system we're all familiar with, Hindu-Arabic numerals. All right, so again, we're going from something alien to something familiar. All right. So let's start with the character set. If we're base 7, we're going to be 0, 1, 2, 3, 4, 5, 6. Remember, it's always one digit shy of the actual base. Okay? You can put commas in here if you like, but that's already pretty tight, right? Anyhow, the number that you see here does not deviate from using this much and this much only, all right? There's no 7, there's no 8, there's no 9, anywhere in this pile of digits, right? Right, in its base 7 form. Okay? How many places are there? How many digits? Right. There are, in this instance, 1, 2, 3, 4 of them. 4 places. So what does that mean? It means that we're going to use powers of 7. All right, we're going to produce 4 powers of 7. And I'll put them over here. All right, 7 to the 0, of course, 7 to the first, 7 to the second, and would be 7 to the third is the 4th example. All right. All right. What do they equate to? I didn't give you on this sheet, I didn't give you the base 4 system, and I didn't give you the base 7 system. Nonetheless, we're going to be looking for positional values that relate to this base specifically. All right? So we'll adapt. All right? And if you have to use a calculator, there's no sin in that. Right? 7 to the 0 is just 1. 7 to the first is 7. 7 squared is 7 times 7, so it's 49. And whatever 49 times an additional 7 would be, 200 something, I think? Maybe I'm crazy. 7, upward pointing arrow, 3. Here's a good point to mention about your calculator. You have a wonderful button on this calculator, the caret symbol. It's an upward pointing arrow, not to be confused with these. That's screen scroll. All right. That will allow you to put an integer here, a whole number value, or you could use something else if you wanted, but 7 to the third equals 343. Wow, I was off. All right, so 343 is the equivalent of that position. All right, that's what 7 to the third would be as a product. Okay, so now we have to adapt a model. All right. Again, alien to familiar, we're going to multiply a lot, but we're going to have to do 4 products that we will then sum together. So, essentially, whatever is sitting in the first position times 343, right? Plus whatever is sitting in the second position times 343, 49. Plus whatever is in that third, well, I'm still thinking left to right, but this digit in the second here from the right would be times 7, and then the last in this train here would be times 1 plus. Right? It would be probably more official to isolate these with brackets. All right. But remember, multiplication, and if you're just doing a multiplication and addition, multiplication is more important in the order of operations. So you really must do all of those first anyhow. Now, let's fill in the appropriate digits and go about our business. All right. 6 is here, so it would be 6 times 343, 0. That one's going to be easy, right? 0 would be here for the second one of these, working from the left. Then there's a 5, and then there's a 3. Right. So, 3 times 1, of course, is 3. 5 times 7 is 35. That's a funny 3. 0 times 49 is just 0. And then 6 times 343 is what? 18, carry the 1, 25, carry the 2, 18, 20. 2058, I believe. Right. And we would naturally have to add these now. All right, so 35 times 3 would be 38. Should be this, all right? The number 6,000, or what looks like 6,053 in base 7 should be equal to, I'm predicting 2,096 in base 10. Remember, these subscripts that are the bases are just a label, right? Superscripts, these are superscripts. They're an operation, right? Subscripts, which is what you see here, they're just more or less a label, right? Something that makes it easier to distinguish what base system you're working with. All right. Let's see if I'm correct here. Yep, 2096. Okay. Now we're going to do base 2. And you have some of that information, as I mentioned, the powers of 2, on at least this diagram. Okay? All right. We're still converting from something arguably alien into something familiar. So we're still following this train of thought, which means we're still doing multiplication. Right? Let us identify the character set of the base 2 system. All right? If we're dealing with binary, base 2 is just an alternative name for this, so it's quote-unquote binary. All right? Then we have just 2 characters that we would be allowed to write in theory, 0 and 1. That's why you see a string here. It's not quite a whole byte. Right? It's just 1, 2, 3, 4, 5, 6 digits. All right? But they're all zeros or ones. So notice the subscript of 2, that is a label. All right? How many digits do we have in this particular case? All right? Let's see. 1, 2, 3, 4, 5, 6. So we have 6 places, which means that we would need a lot of 2s. All right? Up to 2 to the 5th. All right? For the sake of space, all right, let me write that here. All right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. 1, 2, 3, 4, 5, 6 total. All right. Some of these I remember. All right. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. That's a funny looking 4. Sorry, I got a band-aid on. 2 to the third is 8. 2 to the fourth, it would be 16. And 2 to the 5th would be 32. Right. So essentially, what are we going to do? We're going to multiply this first one, and then the second one, and then this 0, and then this 0, and then this 1 again. Can get a little confusing naturally, right? And then this 0 times each of those values that you see in green. So just for the sake of distinction, I'm going to use black. All right? So we're going to multiply this by 32 and then add. And then multiply this by 16 and then add. And then multiply this by 8 and then add. Multiply this by 4 and then add. Multiply this by 2 and then add. And then 0 times 1. And that's the end of the train here. All right. Remember what's going to happen though. The instances of multiplying by 0 is essentially canceling them out of the train. So 1 times 32 is simply 32 plus 1 times 16 is 16. 0 times 8 goes away. 0 times 4 goes away. 1 times 2 is 2. And then 0 times 1 is just 0 as well. So we're realistically adding 32, 16, and 2. All right? Which means 48 plus 2 should be 50. All right? 32 plus 16 is 48, plus that leftover 2 here should be 50. Meaning that 110010 in base 2, subscript, not a superscript, so it's just a label, is essentially equal to, all right, 50 in base 10. This black is dying now too. So there we have it. Very cool. All right. Now, again, in the pile of papers that are available to you, I left this. I swiped it from some other resource. Right. This is helpful if you're on your own and you're looking for something to give you a little bit more confidence. All right. Here's the equivalent of a value of 0 in each of the bases, 2 and 10. 1 and 1, 0, 0, 1 is 1, and then so forth. You see how this evolves, right? More or less the ordinary value and what it equates to in base 2. All right. Okay. Let me get back to that shortcut that I alluded to earlier. Not much of a shortcut, but it's a little confusing, but this document that I was mentioning, it's useful for conversions. All right? Especially when we get to section 4.4. Okay. Suppose you have a number in a certain base, right? And you think it might be the same exact number in what would be the ordinary Hindu base 10, Hindu Arabic base 10 system, the decimal system, right? You could say for sure that this equals this if the conditions are met. The numeral in the alien base is the same numeral in base 10 remember is equals, right? If, right, n, the number here, is less than the alien base, right? So let's just do as an example base 2 here. If it's visible, I will use red. Let's say that this is base 2. And I'm going to put the number, let's just say 1 here. So the number 1 in base 2. So 1 is less than the alien base of 2. Right? And the alien base, namely 2 again, is less than or equal to the number 10. Right? 2 is certainly less than 10, right? So, because that checks out, this condition and this condition, the base is less than 10. The number that is actually talked about is less than its own base. We've met both conditions. Then you could say with some kind of certitude, all right, that 1 in base 2 is 1 in base 10 as well. Right? Right? That is, again, if you feel a little sketchy about it, don't feel bad. All right? It takes a lot of, when you're doing something weird, sort of unlearning things. You have a lot of conditioning, which is you just do things intuitively, right? So you have to fight the conditioning sometimes. Is to confirm 0 is 0 and 1 is 1. All right? So that's going to be helpful when you do arithmetic that involves this, okay? That's section 4.4. Okay. So back to the program here of examples. We're moving on to example 4. Okay, now we're going the other way. Remember, if you're going to start with what is essentially the familiar system, and you're going to convert to the alien system, an alien system, because it's the opposite train of thought, essentially, remember that ultimately you're going to be dividing, okay? And just to reiterate that point from earlier, I have trouble finding all my sheets here. That's it. Okay, we're doing essentially this now. We're going to convert from Hindu Arabic into, because that's what base 10 is, to an alien system, not necessarily Babylonian. Alright, but this train of thought. Instead of calling it Hindu Arabic, we're calling it base 10. Alright, and we're going to convert to base X, whatever unusual thing is. This is the same, this is a more verbal way of talking about something, this is a more symbolic way of talking about something. So base 10, base whatever, right? If this is the train of thought, you are dividing. Right? What does that entail doing as some idea of procedure here? All right. Let us identify the position values of the alien system. All right. These are the things that you're going to be dividing by. All right. Then compare them to the given value, less than, greater than, so be it. All right. When the given Hindu-Arabic number is less than a position value or place value, all right, go to the next lowest place value to divide. All right. That's the most concise way. Is that it occurred to me to type it. There's probably a better way, but anyhow, I'm going to walk you through this as I had done with the Babylonian and Mayan system, and eventually you just do things more or less intuitively. All right. You're going to do the actual division ultimately, and you're going to continue dividing remainders that you get, all right, to the very last position. You want to circle the quotients. All right. That's important because this is going to be part of your answer. That's why I want you to circle the quotients from dividing. All right. Then step 3 would be to, each quotient is going to represent your group. All right. And without actually doing the multiplication, whatever would be sitting here, here, and here in your model, you're going to pile them together. All right. All right. You're going to translate. If you were dealing with Babylonian or Mayan, then you would have to translate at that point the groups that you see into the weird alien hieroglyphics of wedges and boomerangs or dots and dashes, you know. But because the systems that we're dealing with now use exactly the same characters, well, just fewer or more, you know, perhaps some letters, right? It's not exactly the same thought process. All right, so let's continue. All right. So looking at example 4. This is the way that it's typed. If it makes it more clear, all right, I'm just going to rewrite it. It's 486 in base 10. All right, when it's not written with a subscript, you assume that it would be base 10. Always assume. Okay, to base 8. So we want to know what this equals in base 8, essentially. All right, we're going to start again with identifying the positional values of the alien system. So you kind of have to throw a few up there at least to get going. All right. So positional values. All right. 8 to the 0, 8 to the 1st, 8 to the 2nd, 8 to the 3rd. Hopefully you won't need anything beyond that. Here's another thing. We're using the phrase base 8. There's an alternative name for that, right? This, just like the alternative name for base 2 is binary, the alternative name for base 8 is octal. All right, it's the transition between binary and hexadecimal in computers. All right, literally. All right, so let's figure out what these are, and if not, you could always rely on the sheet that I had prepared for you, namely this diagram. All right, I did include some of these at least, right? 512, 64, 8, and 1. Eight to the 3rd is apparently 512. 8 squared is 64 naturally. 8 to the 1st is 8, and 8 to the 0 is 1. So those are the positional values. All right. Sorry. All right. Now we're going to compare the number that we have to these to get going. So we're going to compare, all right, to the given value. All right. So I'm going to do this in bullets. All right. Here's the given value. 486 is less than 512. So we could say we're not going to use that one because it has to be that point at which it's exactly equal to it or greater. So not going to use that, but 486 would be, the next one is 64, right? Notice this switch, right? When it switches, all right, then you divide. Okay? So, if it helps, a little contrast here. 64 we're going to divide into the figure 486. 64 does not fit in 448, but it will fit into 486. We'll have to estimate. All right. If this was 60 and that was 48, then that would be 8 times. So, I mean, if it was 6 and 48, it would be 8 times. So let's try that. I need a little bit of space, so I'm going to do this over here. 64 times 8. Don't ever feel bad if you do extra work unnecessarily. You may end up using it eventually. All right, 4 times 8 is 32, carry the 3. 6 times 8 is 48. 48 plus 3 is 512. All right. So that's overshooting it. So it's pretty close though, right? So what would it have to be? 7. All right. 64 times 7. 28, carry the 2. 6 times 7 is 42, plus 2 is 44. So 448. All right. A 7 above the 6, and we do the long division. 448. Okay. That becomes 16, this becomes 7. 16 minus 8 is 8. 7 minus 4 is 3, and that would zero out. All right. We're going to circle this, because it's going to be part of our answer, and then we're going to continue until the last position value. So we've used this one. Now we move on. All right. So 8 divided into 38. All right. All right. 8 doesn't fit in 3, of course, but it goes into 38, and if you know your multiplication tables, approximately 4 times. All right. And that would be 32. Do the long division. You can use your calculator, especially when you're trying to guesstimate, estimate something beyond the realm of the familiar to you, right? But to get the remainders, you really have to get into it and do the actual handwritten work. All right, so 8 minus 2 is 6, and that zeroes out. We're going to save this digit. It's 4, and we've used that, and continue. All right, until the last position value. So we have, always the last one should be the easiest, right? So just dividing by 1, right? 1 goes into 6 exactly 6 times, right? And it terminates at that point, 0. So we have that, all right? What does it mean? All right, these would be the groups, right, that you would multiply by positional values of 8 to get to the base 10 figure version of the number quantity. All right, this piled together is what it would be in base 8. So I'll just move this over slightly. All right. 486 in base 10, the ordinary number, if you will, is equal to 746 in base 8. It should be. Let's verify. Yes. All right, 746. Sometimes when you're teaching, you make mistakes, but it is important, I think, all right, even if you feel self-conscious, to make the mistake in front of your students. All right, why? Because then they can see that, well, a person that made a mistake can also do something correctly, right? Namely themselves. All right. Thankfully, I didn't screw that up there. Nonetheless, all right, moving on. We'll continue. let's do example 5. We have 5, 6, 7, and 8. Dancing. And then we're done for the day. Okay? We are going to now convert 273 to base 3, right? I don't know if there's a special name for base 3. I haven't come across it, but the logic is still this. We're converting from something familiar to something alien, so we're going to divide ultimately. All right? If you see 273 without any subscripts, right, you assume it's 273 in base 10. Okay? And we are naturally going to then figure out, well, what is that in base 3 then? Because that's what they're requesting. We're going to figure out the positional values using base 3s, right? So throw a few up there to get going, right? Unless you have a reference someplace. 3 to the 0, 3 to the first, 3 to the second, 3 to the third. Might need another one. So I'm squeaking it in here, but 3 to the fourth. All right. Alright, so 3 to the 0 is just the amount of 1, 3 to the first is naturally 3, 3 squared is 9, 3 to the third is 27. So what's 27 times an additional 3? 21, carry the 2. We might need more than this actually, so let's see. 6, 8, 81, right? 3 to the fifth, hopefully not going to be something beyond that. 81 times 3. 3. 3, yep, 243. Okay. I would bet that if we did another one, which just to get you comfortable, 3 to the sixth, we would have something much larger than that. So let's do 3 to the sixth. And you see, yeah, 729. You only need it for a frame of reference, really. Alright, so we're going to compare to the given value here. Each of these. Given value of 273 is indeed less than 729, so for sure we're not using that one. What about 273 compared to 243? Right? This is greater, this is the point at which it switches to that. So we're going to use this to divide. So 243 into the given value of 273. We'll see how much we can get. They're reasonably close. There's a difference of 30, right? 243, you put a 1 here, and then you subtract to deduce the remainder of 30. Circle this because it's going to be important to the answer. And then you continue into the last position. Now, this one's a bit more of a nuisance, but we'll see. 243, we use that. Alright, watch what happens in this case. It might seem like you're getting in trouble, but you're not, right? 30 is the remainder. So we have to check each position, so we're going to go step by step through it, all right? If 30 is the dividend, essentially, and the position value is now 81, we have to check it, all right? Does 81 fit into 30, or is this too small? It's too small. So don't be deterred, just go, it is what it is, right? I'm going to put this in red just for this distinction. It's 0, right? 0 times 81, you'd put a 0 here, you'd subtract, and you'd still get stuck with 30, all right? nonetheless, this is part of the answer, right? That position is just 0, right? Fourth, then continue, right? 27. Now you have something that's going to work, all right? Now we do 30 divided by the next position value, which happens to be 27. All right, how many 27s can you fit in 30? 1 and no more. So you put a 1 here, and you subtract, and you get 3. All right, circle this because it's important to the answer. And then I'm a little shy of space, so I'm going to write some of it elsewhere. From here, because I need the space, all right, I'm going to take that 3 and I'm going to divide by the next position. I just use 27, and I'm going to get the same issue again, right? I'm going to have to use 9, at least checked initially, and I'm going to go, wait a minute, 9 doesn't fit into 3. That doesn't mean that you don't put anything, it just means that it goes in 0 times. 0 times 9 is 0. That's how you would always do long division. Right? And then you get 3. Right? Same remainder naturally. Right? And then you continue in the train of thought. Right? You've accounted for that, move forward. Right? So, now you have 3 divided by something that would work technically itself. Alright, in this instance. So how many 3's can you squeeze into 3? Exactly 1, right? Which is 3. And the difference is 0. Right? And you circle this and this because they're going to be part of your answer. All right? And you continue until always the last position value. So you have the remainder that you just got, 0. The position value of 1, that's your divisor. 1, how many 1's can you fit into 0? Exactly 0 again, right? It doesn't really work, right? But it's 0. Well, it works in this respect of 0 times 1 produces 0, and then it terminates, right? So it's a little goofy. Now, if you're wondering, why is this one such a pain in the neck? Because remember what the character set looks like. The alien character set that we're working with is base 3. So that means that the only thing that you'd be allowed to write the quantity in base 3s would be the digit 0, the digit 1, and the digit 2, right? That's why you see notice 1, 0, 1, 0, 1, 0, right, as your answer, right? Put them in the correct sequence. I know that unfortunately you have to read sort of it counterclockwise here, but that's the first digit. So it's 1, second digit, 0, third digit, 1, fourth digit, 0, fifth, 1, last, 0. The number, the ordinary number, 273, is 101010 in base 3. It just looks weird because that's how many, the only things you're allowed to use. 2 just didn't get used. Okay. So here is to confirm. Yuck, right? It's correct, all right? 10, 10, 10, all right, in sequence, all right? All right. Now we're going to do base 12. This is where you start seeing letters. I spell my name with numbers, right? That would be funny. Now imagine you're spelling out math with letters. You are, right? That's what happens when you get to base 12. We're going to go back the other way for the moment. Right. If the train of thought is now reversed, it's going to be alien system, because base 12 is indeed alien. Alright. Alright, to familiar. Now again, remember, you're going to multiply a lot. Okay? So we're going to go back to those procedures. Alien base 12 into base 10, which is familiar. Right. My red is dying. Oh, red, cooperate, would you please? Alright. Let us go through this process. If we're dealing with base 12, what does the character set look like? For base 12, alright, always start with 0. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what would be 10 and 11 is the letter A and the letter B. Okay? I'm just going to squeak it in here. This really is 10 and that's really 11. Notice again, because it's base 12, we have 12 characters total, but you don't write that in the set, right? The number 12. All right. Let us establish some position values now for base 12. All right. It's a bit of a nuisance, but we must do that. Incidentally, there's a name for this. Duodecimal is base 12. Damn it. Died. Okay. So I'm buying markers later. Okay. What are the position values? All right, of base 12. You kind of have to write from the right side, so that kind of is annoying. 12 to the 0, 12 to the 1. I don't think we're going to have that many. 12 squared. Maybe we can get away with 12 to the third. All right. 12 to the 0 is naturally 1. 12 to the first is just itself 12. 12 squared is 144. All right. 12 to the third is 144 times 12. So let's just, for the sake of expediency, do that. 12 to the third. 1728. Okay. So 1,728. I don't think we're going to need that. Okay. Let's write out the model now. All right. How many places do we have? Number of digits. Well, there are, including the letters, 1, 2, 3, 4 characters. So we need 4 places to account for. Right. So we're going to need 1, 2, 3, 4 of these, it seems. All right. So there's my new red here. It's black. We're going to use the number 3 for that digit times 1728 plus 9 times 144 plus B times 12 plus A times 1 rather. Alright, now because it's weird, alright, that we have letters showing up here, to do the actual arithmetic, what are we going to have to substitute B's for? Alright, that's really going to be 11, and that's really going to be 10. So the easier ones are 10 times 1 is just 10 naturally. 11 times 12 is 132. Alright. And it's going to be 9 times 144. Alright. 9 times 144. This is 1296. And 3 times 1728. 5184. 5184 plus 1296 plus 132 plus 10 is equal to 6622. That means that 39, just to make this really obvious, 39 BA in base 12 should be equal to 6622. 6,622 in base 10. This is the end of the small group. Okay. Let's see if I'm right. Yeah. 6622. There's a second part to this question. Okay. What we're asked to do for part B here, which I skipped, is now, alright, I made it example 7, sorry. Whatever. Let me, because it's getting a little redundant now. Let me do what is part B. Alright, which is to convert this now to base 12, because we're going to have to get comfortable with using letters. Alright, where it would seem odd to be doing that. And I'll do a base 16 hexadecimal version of this. Okay. Alright. Focusing on that. Alright. What are we doing? We're converting from what is familiar to what is alien. So we're going to multiply. Let's establish again the character set for base 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, with commas in between. This is base 12, aka duodecimal. The position value, well, how many digits are there? 1, 2, 3, 4. What am I doing? I have to correct myself. When we go from familiar to alien, we are dividing. Sorry. So, let's establish the position values. 12 to the 0, 12 to the first, 12 to the second, 12 to the third, 12 to the fourth. Hopefully that would be sufficient. Okay. 12 to the 0 is 1, 12, 144. I've already forgotten, 700 something. 12 to the third, 1728, sorry. Which is maybe the what we're going to use, but we'll check by doing 12 to the fourth. Yeah, right. 20,736. Okay. You always kind of have to overshoot it, unfortunately, when you're doing your comparisons. All right, we're going to compare now. All right. The figure that's given, 6,893, is less than 20,736, otherwise known as 12 to the fourth. So we're definitely not going to use that. All right. That's the barrier. 6,893 is going to be greater, thankfully, than 1728. So this is where we're going to start. Right? Or if it was equal, we would do that too. Right? So I don't have to bend over. 1728 divided into 6,893. Okay. Let's see if any of these numbers look familiar. If that was about 2,000, and that was about 7,000, just to round up, all right, then it might be about 3, all right? So even if the estimate is not accurate enough, don't feel bad if when you're doing your calculations you multiply unnecessarily. You may end up using it anyhow in some cases. 8 times 3 is 24, carry the 2, 8, pardon me, 6 plus 2 is 8. Then 21, carry the 2. 3 times 1 is 5. 5,184. That's probably as close as you're going to get. All right. So if you did another 17 to this, it's already going to exceed the digit. Would be 6,800. Yeah, it's going to exceed. So 3, right? And you're going to subtract that figure, 5,184. That becomes 13. This becomes 8. 13 minus 4 is 9. 8 minus itself is 0. 8 minus 1 is 7. And that's 1,709, which is kind of sucky, but that's the first digit. All right, so 3. Then we continue. We've accounted for using this. Now we're going to move on. All right. Next one. 1709. And we're going to divide by the next position value of 144. All right. 144 into 170 is just about one time. So 1. 144. Subtracted from that, this becomes a 10. That's a 6. 10 minus 4 is 6. 6 minus 4 is 2. That would zero out, break down to 9. 144 times 2 would be 288, which would be overshooting this. Alright, so it's going to be 1 again. 144, and we'll just have a significant remainder here. 9 minus 4 is 5. 6 minus 4 is 2. 2 minus 1 is 1. Right. This is a sucky number, but that's what we have. All right. And eventually we're going to translate that into the letter B. Right. Because that's the character set we're allowed in the alien system in question. So moving on, we now have to do 125 by the next position value, which is 12. This is really dying, this poor marker. I should just throw it out. 12 goes into itself exactly one time, which terminates, but you have to bring down 5. How many 12s can you fit in 5? 0. Just to get that out of the way. I don't want to get confused. 0 times 12 is 0, so you're left with a remainder of 5. This is again double digit answer, which again we're going to eventually have to substitute. Okay. And we have to do one more position, which is easy, right? So we're just going to divide this remainder by 1, which is 5 divided by 1, which is just simply 5, and it terminates, as it should, always on the end. All right. If you don't get that terminating, I'd be putting it in question. All right, so the original quantity I'll put it down here. 6,893, which is base 10, would be equal to these things piled together. They would be groups. Otherwise, it's 3, what would be 11, what would be 10. I'm doing double digits in parentheses just because it's a little pocket that we're going to have to change. In base 12. So I'm going to put a little subscript 12 here. All right? Because you're working in the character set of duodecimal, all right? 10 is known as A in that system. 11 is known as B. So you really must put an A here in place of what would be 11, and a B here, pardon me, vice versa. A B in the front, and an A in the back. So, yeah. To make it a little bit nicer to read. 3BA5 subscript 12. And that should be your answer. Right, just to verify. I must have cut it off. Yeah, there it is. It's in the middle here. Basically right there. 3BA5 base 12. Okay. I don't know why they didn't make it more proud than that, but hey, whatever. Alright. Alright. Let me show you just part B of this next thing, because we're going to be dealing with, that's hexadecimal. It's a little strange. So we'll go through the logic here. I just want to do this one. We convert the regular base 10 number, which is familiar, 6317 base 10, into what is alien, something in base 16. So again, if we start with the regular number, we go to alien, we're going to divide. It's arguably more difficult to do this process going backwards. Let's establish what the character set is for base 16. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for what would be 10 is A, what would be 11 is B, what would be 12 is C, what would be 13 is D, what would be 14 is E, and what would be the maximum of 15 is F. So kind of goofy, right? But just remember, that's 10, 11, 12, 13, 14, and 15. All right. So if we're base 16, the numbers can get rather large, right? But let's identify some position values, okay? Because we have to compare. All right, so 16 to the 0, 16 to the first, 16 squared, hopefully not much more beyond this. All right. How many digits do we have? It's not a question because we're not starting with the alien system. So 16 is 1, 16 times 16 is, let's see, 15 times 15 is 225, I believe. So let's see, it's beyond that. 16 times 16. 256. 256. Alright, looks like we might need something significantly beyond that. So what's 256 times another 16? 4096. That's probably what we're going to start with. 496. Let's just do another one to confirm. 16 to the 4th times 16. Yeah, it's 65,000 at that point. 65,536. So yeah, way over the threshold here. Okay. Anyhow, we compare at this point. All right. The figure is 6,713, which is significantly smaller than 65,536. So we're definitely not using that. All right. But 6,713 is greater, or equal to, in this case, it's greater, 4,096. So we're going to start here. Okay. My black is really dying, so I'm going to use blue a lot more. Alright, so 4,096 into 6,713. You'd only fit about one of those in there. So that becomes 13, that becomes 0 temporarily. 13 minus 6 is 7. This becomes a 10 once I diminish this to a 6. 10 minus 9 is 1. 6 and 0 is 6. And that's 2. Alright. Save that. Next one. Let's see. 2,617 by 256. 256 fits into 261 very close, so put a 1 there. Subtract 256. The difference between them without doing the borrowing here is 5. Alright. And that means that this is 57. Alright, just to verify, that's 11, 5, and that's 0 and 0. Good. Alright. 256 does not fit into 57 though. Alright. So we will have to put a 0 here. 0 times that would be 0, and the remainder would be 57 nonetheless. Alright. Circle that. Alright, we continue. 57 divided by 16. 16 goes into 57 probably about 3 times, which would be 48. Alright. The difference is, let's see, 17, 9. Alright. And that's the end of that without doing decimals, of course, so we're going to save that. And do this one more time. 9 divided by 1, which is just 9. Okay. 9, perfect. Okay, so good. Just for the sake of space, let me erase this up here. So, part B, right? 6,713 and base 10 really is equal to apparently 1. What is a 10? Because it's 2 digits, I'm putting it in parentheses to remind myself. 3 and then 9 in base 16, otherwise known as hexadecimal. Alright, and because we're not allowed to use this sequence of characters in hexadecimal, we're going to look for the equivalent of 10 in the character set. It's A. So there should be an A here. So 1A39 subscript 16. Let's check on that. Where did they put it? Yep. 1A39 subscript 16. Okay. Alright, let me turn off the projector and I'll just remind you of something. Okay. And we'll get busy leaving for the day. Alright. Okay, for homework, please do section 4.3 in my lab. And if you do that, you're right where you're supposed to be. Okay? Alright. This is again for, let's see, Thursday. Alright. I'll see you guys on Tuesday that follow. Pardon me. This was for Wednesday. I'll see you on the following Monday. Okay? Thank you for listening. Be careful out there with the snow.